Hi, I'm Srivarshini Ganesan, and I'll be presenting my term project for the course Classical Molecular and Materials Modeling. My project explores how one can quantify free energy difference from non equilibrium work measurements using the Jarzynski equality. Let me begin by introducing what a steered molecular dynamics simulation is. This is an enhanced sampling method where an external force is applied to specific atoms or molecules to study their conformational changes. This simulation technique is used for simulating processes that occur on timescales that are too long for studying with a conventional MD simulation. For example, if you have to study a protein unfolding or a ligand binding, it's highly possible that the system is trapped in a local minima and doesn't have sufficient energy to cross over a barrier and sample the other minima of the free energy surface. Um, but in a steered molecular dynamics, the external force that we are applying on the atom gives the system the external energy to cross over the barrier and sample the other states. There are two types of steered molecular dynamics simulations, a constant force or a constant velocity simulation. In the constant force, an external force is directly applied on the atom or set of atoms of interest, while in the constant velocity type of simulation, a harmonic potential is applied and ensuring that the atom of interest is eventually moving with a constant velocity. So, this SMD simulation imitates the atomic force microscopy experiments and can be used to understand what's happening in these experiments and for understanding processes like protein unfolding or ligand binding. Now let me introduce the Jarzynski equality. This is a mathematical relationship that connects non-equilibrium work to equilibrium free energy difference. So as we can see in the cartoon depiction here, if we have multiple non-equilibrium work distributions, an ensemble average of the exponentiated work with the Boltzmann factor would equal the exponentiated free energy difference. So, with this equation, we can go from non equilibrium work measurements that are obtained from a steered molecular dynamics simulation with multiple realizations of the work. We can go from these work that we have calculated to the free energy surface that we are interested in understanding. Now let me describe the simulation setup that I have. My simulation box consists of 100 argon atoms that are randomly inserted, and I use periodic boundary conditions to simulate bulk effects and to also avoid the finite size effects. In periodic boundary conditions, the particles do not see the walls of the box and they are able to cross the boundaries. And once an atom crosses the boundary, its image enters the system uh, that we are looking at. And I also implement the minimum image convention so that the every atom only interacts with the closest image of all the remaining atoms in the system. Once we have initialized the initial positions, the initial velocities of these atoms are sampled from a Maxwell-Boltzmann distribution, and the system I'm simulating is at 298 Kelvin. So the velocities are assigned according to that, so that it's easy for the system to equilibrate to the desired temperature. The interactions between the argon atoms are modeled with a simple Leonard-Jones potential given according to this equation. The dynamics of the system are propagated to the velocity Worley algorithm, and I'm also equilibrating the system at a constant pressure and temperature by coupling it to a Berenson thermostat with a coupling constant of zero point 0.1 picoseconds and a Berenson barostat at 200 bar with a coupling constant of 0.001 picoseconds. The system is further equilibrated at NVT conditions with a Berenson thermostat with a coupling constant of zero point 0.5 picoseconds, and this is also done for 5 picoseconds. And then the steered molecular dynamic simulations are carried out by either applying a constant external force or a constant or keeping the pulling the particles at a constant velocity. And this is done for one atom and this is done for zero point 0.5 picoseconds. Now let me explain how I calculate the work. For the constant force pulling simulation, the work is calculated as the integral of the force, external force that's applied times the displacement. And since we are doing a discrete time steps, it's just the force applied at that particular time step times the displacement in the direction of the force. For the constant velocity pulling, the force is given by the spring constant times this target velocity times time step minus the initial position, and the work is the average force times the displacement, and the average force is just the mean of the initial and the final forces. This cartoon here shows that you can imagine that there's a dummy atom that's pulling the target atom with a spring constant k and the desired velocity v. Uh, In this slide, I show that the system has been equilibrated at the NPT conditions and the energy equilibrating to a particular value, the kinetic energy, the potential energy, and the temperature equilibrated to 298 Kelvin, the pressure uh, uh, reducing from a initially higher value to about 200 bar, and the length of the simulation box increasing and then eventually equilibrating to around 2.7 nanometers. I also look at the equilibration at the NVT conditions, and here too we see that the system has equilibrated really well, and the box length has not changed in the NVT system. In this slide, I'm looking at the work distributions in the multiple realizations. So, in this tiered molecular dynamics, typically one has to do multiple such non-equilibrium simulations, starting from multiple different random initializations of the simulation box and equilibrating each of these systems, and uh, applying the external force on the target atoms, and then calculating the work and using the ensemble average as described before, calculating the free energy. But here I have used another approach where I'm taking the same equilibrated box and applying different magnitudes of the force on the same atom, and then calculating the average, ensemble average of the exponentiated work. Uh, so the different uh, lines here, the green one corresponds to a force magnitude of 50 zeta joules per nanometer, and progressively increasing the force magnitude, we see that the work uh, done is higher as expected, and the equilibrium free energy is this black curve that's about minus zero point zero 0.02 zeta joules, and the graph on the right is for a constant velocity simulation, and here too the constant velocity that I've targeted is progressively increasing from the green curve to the cyan one, with 10 nanometer per picoseconds to about 50 nanometer per picoseconds. And here too, the free energy that I have obtained from the ensemble average of these five work distributions, we can see that between these two simulations, as we have started from the same equilibrated system and we are pulling the same atom, the free energy curves seem to be similar. Like the scales are different on the two graphs here, but the equilibrium free energy is minus zero point zero 0.02 zeta joules in both the cases, and there seems to be some consistency between the two um, constant force and constant velocity pulling simulations. Here I'm looking at one atom that's being pulled, the red atom, with a constant force along the x dimension, and we see that the system has um, the VMD simulation actually depicts how the atom has been pulled with a constant force. Thank you.